This is Dive into Magenta. I'm Attila, Szasz.
And I'm Gergo, Hosszu.
And before we start, just a quick intro. We work for a company called Szasz, and what we mainly do these days is embedded security evaluations. So, routers, IP cameras, set-top boxes, and stuff like that. And the company is also involved in EU research projects. We have 3 ongoing ones, and all of them is in the field of CPS and IoT security. So, quick overview of what we are going to cover today. We researched a new operating system called Fuchsia as a free-time project. So this was not done really in the company. And we decided to port 2 tools which are proven to be successful in the Linux case. So what we have is the kernel address sanitizer port, which we call MSKSN, and it is working for heap allocations now. And we also have this tool called Syscaller, which we will talk about. What we have now is a rudimentary fuzzer that uses this thing called Sankov coverage, which Syscaller is also based on, but Syscaller has also other nice features which we don't have yet. And obviously, we'll have other general observations on this new kernel, which is called Magenta. So, what is Fuchsia? So Fuchsia is a new operating system developed by Google, and although it has surfaced the internet around a year ago, no one really knows where Google is going with it. So lots of speculations is going on, and they didn't announce anything on the I/O this year. So still, we don't know what it is about. But the development is open source. And why is it interesting from a hacking perspective or technically? Because it doesn't use the Linux kernel. Actually, they developed a new thing from scratch. And when someone is developing something from scratch, we might hope for some security issues. Okay, so Fuchsia, Magenta, and friends. Fuchsia is the whole operating system, while the kernel is called Magenta. And actually, this was a little bit a problem for us because a few weeks ago they changed the name to Zircon because they have this library called Magenta for machine learning and stuff like that. And probably because of that, it is now called Zircon. But we kept the name Magenta. So you can see this commit log that basically the name has changed. But anyway, this is open source. So you can see the code and the Git log. So you can guess which direction they are going. And this is kind of weird because we don't really know what this thing is, so what their purpose is with it. It seems to be a complete operating system for PCs, tablets, and mobile devices. But there are lots of inaccurate blog posts you can find which are speculating on whether this might replace Android someday or may replace Chrome OS. And so don't trust them until there's an official announcement. The actual code is on around 200 repos, so you can find it. They have nice logo, and most of this is, well, half of it is third-party libraries, of course, because even Google can't develop everything on their own. So why are they doing this new kernel from scratch? There has been some speculation that actually it has to do something with licensing, because the code doesn't use GPL. Instead, it's like a mix of non-copyleft licenses, like BSD, MIT, and Apache. And what we found that it actually limits their choice in third-party libraries, because as probably you know that you can't really integrate GPL stuff into something that is going to be released under MIT or stuff like that. I'm not a lawyer. So, for instance, they have this libc called Maso, and there's a network stack called Lightweight IP that they use for their initial efforts in implementing a network stack, and these are MIT-style licenses. So, Magenta is a set of core OS services. There's a big ecosystem built upon it. So, you have Mojo, which is a collection of IPC services, providing higher level abstractions. I'm guessing it is something like Binder in Android, but I'm not really sure. You got Magma, which is a framework for graphic drivers in the kernel. You get Azure, which is more 3D oriented. It's a physically based renderer. The main compositor is called Mozart. So Mozart would be something similar to what Wayland is in Linux. And all of these components enable them to use this OS-independent library for application development called Flutter. And actually, you can write applications for Flutter in Darts, which is also a Google product or technology. Okay, how does it look like? So tech blogs are certainly interested in the look and feel of it. This is kind of how it looks like, so like a vertical scrolling page, and they have this style in Android, which they kept this nice Google minimal style. But you know, we are system software guys, so we are interested in this. This is the kernel booting up with the address space regions showed. So let's look a bit under the hood. So first question, which programming language is it developed in? So in the past, usually, kernels were developed in C. So this looks like an obvious choice, like Magenta must be written in C, right? But actually, no. Magenta is written in C++. And you know, as a Linux guy, I have to mention that there are certain high-profile guys who might dislike this choice. All right, but anyway, this is Google, so they are, you know, very smart. They use a modern subset of C++, to be frank, but of course they have to allow and disallow certain features and functionality. These things are allowed. I'm not going to read them. For me, it's nice that they have lambdas. It's kind of cool in kernel code, and the usual suspects for things that are not allowed in kernel are like RTTI, of course, and exceptions, inheritance, like, you know. They don't use the standard library either, but they have a template library called mxtl, and it implements, you know, the usual stuff like containers, smart pointers, things like that. Actually, they also rely on WAVR trees for many things, and they have like nice little utilities. So let's look at some code. This is the page fault operation, where, you know, of course, you have to make sure that when you do page fault, that the underlying bookkeeping structures are synchronized. So here's a lock, a mutex, and actually you just have to declare this autolock, and when it goes out of scope, then the mutex is unlocked. So throughout the page fault operation, you are logged and you are fine. Another thing, this is a lambda. It's used for calculating some nice counters for every page. I thought it was cool in kernel code. Now this is another thing. This is more interesting. So here is some comment. This is basically using a function of a more derived class and some hackaround to get to this function. So this is okay, that's fine, it happens. But this function goes on, and you find this. And now this is interesting. You can read the comment. So basically, this is smart pointer semantics, that a reference is leaked here, which should be, you know, like a high-level concept. But in this particular case, it's a VMO, which we'll see is an object for managing virtual memory itself. And they design the code so when a VMO is destroyed, the MMU is queried and updated, and actually the TLB and the page tables are updated. So this one particular code is actually doing something low-level nasty stuff. So it says some side effects which are not expected from something like a smart pointer thing. So actually, I was wondering whether this guy is right after all, but you know. So yeah, now to Magenta being a microkernel.
So a quick recap, Magenta is a microkernel. This means the essential thing is actually in a kernel space. In monolithic kernel, you have almost all your services and functionalities. Yeah, and it's also a big, huge monolithic kernel. Yes. And what's about the advantages? The principle of the last privilege, basically the components as well are isolated. The kernel attack surface is reduced, and there is a high fault tolerance. Since the subsystem can be restarted, while in the whole monolithic case, one bug can bring down the whole system. So it's easier to distribute architecture, and yeah, that's... So guess who said it? Okay, so actually Magenta is based on even a simple system called LK, which is a little kernel. LK is a tiny operating system written by Travis Geselbrecht, who is the tech lead of Magenta. LK is used for bootloaders and other applications as well. Magenta creates a wraparound LK's primitives, and this is a small set of implemented C++ objects. And here comes the question, is this POSIX compatible? It's not a goal, but the C library provides it. And libc creates the illusion to traditional system facilities, although they might look very different from under the hood. Yes. So the Magenta works quite differently than Linux. Kernel objects are referenced by handles, and the handles have associated rights with them. Handles can be thought as a session or a connection to the particular kernel object. However, a single handle can be bound to a single process, bound to a kernel. When the bound to a kernel, we call it in transit. And when it's not bound to a kernel, we call it it's visible to user mode, sorry. And there are many system calls that create a new kernel object and which return to handle it. And you can find here three syscalls: mx event, mx process, and mx thread create. Channels are from IPC basically. They make it possible to send around handles especially. Channels maintain an order of queues of messages to be delivered to either direction. The message consists of some amount of data and some amount of number of handles. Call to mx channel write enqueues one message, and the call to mx channel read dequeues one message. The first, and there are two steps how the process is going. The first is automatically write the data into the channel and move ownership to all handles in the message into this channel. And the other one is almost the same. These are the main objects managed by the kernel. So you have the IPCs, signals, and task-related objects. You can find channels, sockets, FIFOs, events, events pair, futex, which is the same as mutex, task, processes, thread, and all the stuff. Yes, and handle can be thought as an active session with the specific OS subsystem scoped to particular resources.
All right, so some example of this. The Magenta kernel comes with a minimal RAM disk, basically, and it has a PS utility. And so we looked at how the PS utility works. So in Linux, it would probably involve using the procfs. And in this case, to have access to the processes, the PS utility's process actually has to acquire a handle to the root, something called a root job. And this is done in the following way. So there's this device node called sysinfo, which is something similar to proc in Magenta. And sysinfo can actually provide this handle to the root job. But how does sysinfo have it? Sysinfo is basically a driver, and all drivers are sort of managed by this other user space component, basically one of the core services called device manager. And during boot, a device manager receives this root job handle, which it keeps, so that it can actually duplicate it when some other process requests it. So here's the code. So basically, PS does this. So it would like to walk the root job tree in order to show you information on the processes. But in order to do that, it has to acquire this root job. So it opens this device node called sysinfo, dev misc and sysinfo, and it issues an ISCTL to receive the root job. So how does it provide actually the root job? Of course, it has it through the boot process, and actually it has to duplicate its own and return it. But there's a trivial issue, and I don't have a zoom here, but what happens is that this handle is copied with the same rights that the device manager has. And of course, the device manager is kind of a critical component, so it can basically do anything with the root job handle. And this is the trivial issue here, and even the developer noted here that this should be constrained to enumeration rights. That is, that the handle, through the handle, you should only be able to list the processes, but you shouldn't be able to actually create one and things like that. So now on to security features of Magenta.
Okay, so these are the security features Magenta provides it. It handles object design that we saw is not just a random design decision. We see it provides interesting security characteristic. It has something called safe stack. We also have ASLR, which is a more familiar protection, and we have another nice things. We will discuss it later. And yeah, it's also there, but it's not questioned in these days. So, safe stack. It's a modern security feature in LLVM. No more stack cookies, which is good. Protects against stack-based control hijack flow, and does not change the ABI. So the capsule summary, what is the safe stack, is each thread has 2 stacks instead of 1. Safe stack and unsafe stack. The unsafe stack is used for all purposes where the pointer into the stack memory might be used, while the safe stack is used only to purpose where no code should ever see a pointer into the stack memory. So unsafe stack is used for arrays or variables. And yeah, also the well-known ASLR, it's just a quick recap. It's an address space layout randomization, Linux specs project, Foursquaring it, July 2001. And ASLR, it's a quick explanation. It's randomizing the base address of the loaded binaries whenever it's possible. This prevents attackers lying on fixed addresses during exploitation. As we can see here, every start they randomize the address layout. All right.
Okay, so Magenta is a microkernel, and there's this thing invented by microkernels called capability-based security. And it shouldn't be confused with POSIX capabilities like capsysadmin and stuff like that. It's an entirely different thing, and it is actually a design principle. So we have this problem that in traditional models, the process has an associated privilege, which is, in the past it was the user ID, but now we have capability sets as well. So this is, kernel has this structure, as you probably know, called cred, which is stored in the task struct of Linux, in the Linux kernel data structures. So there's a problem with that. You can end up with processes having too much privilege, and actually that's your main task when you are hacking something, to make the process do something it shouldn't do. And if it has UID 0, then you have probably made some nice privilege escalation if you could hijack that process. So capability-based security tries to solve that and limit the process's privilege to the minimum. And the way it works is basically by encapsulating objects with rights and privileges and passing around these capabilities. So these are handles in Magenta. So this is useful for sandboxing processes, providing isolation. So if you want to have an isolated process, then you have to make sure that it only has handles with limited writes. Also note that the notion of user identity is weakened a little bit by this, because you have all this kind of, so it looks like sort of a distributed algorithm, and it's more complex. There's no easy definition of a user identity on the process level. And Magenta has also other hardening tricks. There's one thing I found. They have this container in this template library called Arena. And Arena is used for storing objects of the same size. So it's very efficient. And also it's very secure, because what they do is they separate control structures and data. So metadata and control structures are not interleaved with data. So why is it good? Basically, when you try to exploit some kind of heap primitive, you're trying to get some information on the allocator, and you probably want to hijack some control information that the allocator itself uses. And of course, one main way to do that would be through some overflow. But actually, Magenta puts a guard page between these address regions. So you have the data here, and as you can see in the command, there's an unmapped guard page, and then you have the data. So you have the control, unmapped page, and the data. So even if you have an overflow somewhere, you can't overwrite control or data, vice versa. There's another thing. Every object basically embeds a little canary, or a magic value, and each function of the function, each function corresponding to that object, that is usually the class or some other C function that uses this object, it starts with an assertion that the magic value should be what it is supposed to be. So why is it good? Because you can detect user freeze. And this is not really a countermeasure, but it is something they do. And as you can see, for the address space basic structure, you have this magic value. And for example, the MMU function starts with asserting that the magic value should be the one expected.
So how the heck these things? It's a moving target since the code is evolving so rapidly. So let's think about this. First idea regardless of capabilities, the syscalls interface is important. Let's explore successful Linux things and try to port a syscaller. All right, so let's hack. First of all, becoming root is not possible. Yeah, I mean, it's a local privilege escalation now means that handlers have to be compromised somehow or obtained. So if we can execute code in kernel mode, then we are likely to succeed. To attack the kernel is only an option, but we would like to attack with syscalls. And let's see three syscall. This is the three categories. Just for a note, the second one is the main one, and those syscalls have higher complexity, so we should attack those. Yeah, it's fuzzing. I guess everybody knows how does it work, what it's about. Here is a Wikipedia definition. So, essentially, this is what we are trying to do, to feed some syscall with bad parameters. And also, not just one syscall, but potentially a chain of syscalls that might trigger more interesting behavior.
All right, so this is my big picture of coverage-guided fuzzing. Basically, ideally, you would like to have a fuzzing loop which finds a new bug in each iteration, but this is, of course, not possible. But what is possible, let's say you have some knowledge of the program structure, say coverage data, you can randomly wander around and use this feedback to guide you and take the right direction. So for example, here's the code on the left, which is a lottery function. And if you were just trying out random values, then it would be an exponential problem in the size of the numbers. But if you have coverage and know that nested structure here, it tries to emphasize the potential coverage info coming back from these branches. So say you're fuzzing this, and you get feedback that actually, okay, something happened here because the first number is this. And then you can use this to generate other use cases, to generate other possibilities. And now that you know an interesting test case, you know where to go. And from the first number, you would easily get to the second one and the third one. So in some cases, it actually makes that from an exponential problem, you can go into a linear one. So there's this tool, no fuzzing talk without it. It's called AFL. It basically invented feasible smart fuzzing. You know, sales pitch here, sophisticated, smart, fast, rock solid, and actually this is true. But there's a problem with it. It's not really useful in itself for kernel fuzzing. It's more suited for testing smaller libraries, but still there's some work going on to make it better suited for this. So for example, there's this fuzzer called 3-force AFL, which basically a QEMU in full system mode, which spans up a fork server and uses AFL to fuzz actual kernels or any system software you wish, at the cost of being a little bit slower. And also we know of this Oracle project where they used AFL to fuzz file system parsers of the kernel or file system handling of the kernel, and with quite nice results. So there's another approach here. There's this tool called syscaller, which is actually designed for system call fuzzing. It is developed by Google, and it has found a huge number of vulnerabilities in the Linux kernel already. So the way it works, it uses a declarative syntax for system calls, which captures the input structure already very well without any coverage info, but it also uses coverage info called sanitizer coverage. This is somewhat weaker what AFL uses, because AFL uses edge coverage, and this is more like block coverage, but it still makes it a very smart fuzzer. So how to use coverage for fuzzing? Basically, you start out with an interesting corpus, so you have to have some nicely structured data to start with, but then you can mutate and execute input from the corpus, the usual ways like bit flips, stuff like that. And if input gives new coverage, you try to minimize the test case and add it to the corpus. And this way you end up with a natural genetic algorithm, or like evolutionary algorithm, I would say. And this is what we basically do. And this is from the LLVM documentation. This is what Senkov is. It's tracing pieces. So LLVM inserts functions into the basic blocks, and you can implement those functions in your runtime. So you can retrieve the PC addresses that were at those points. So our tool does exactly this, implements those callbacks in the kernel. In the Linux case, this is done by the kcoff patch, and we try to mimic this. So this is how kcoff looks like. So first of all, it creates this sysfs device node, basically, kcoff, and you can use it to share a buffer with the kernel, so you can retrieve the coverage data, and you can also issue IOCTS to initialize it, enable it, disable it, and stuff like that. So we try to mimic this in Magenta. We also have basically this, so we have a shared coverage data buffer, and we can do basic management like enable and disable. What we don't have this declarative style of syscaller. Syscaller is written in Go, and I don't know Go, and it made made hard to really understand what's going on with that. But we have something like a serialized one. So we have a brief format for system calls and arguments, and actually we use fuzzing on this serialized data and then turn it back to actual syscalls. And what we do is basically bit flips, arithmetics, non-integers, and we use this coverage info to guide us. So results, unfortunately, not so much, but remember, Magenta is a moving target. So when we found some crash, and we tried it on the latest commit, it didn't crash anymore. But we have some nicer ones. So after the applications, we have some interesting ones like this. So these are two syscalls used for managing virtual memory objects. Here we create a legit-sized object, and with certain funny values, the kernel crashes. And it actually looks like something like a use after free. We're not sure yet, so we have lots of stuff going on. And we expect more results with MXKSM, this other tool we developed. And we also expect more results with syscaller itself, because syscaller now is being added future support. Anyway, we are the first to do this, and it still feels okay. But we had this another thing.
Yes, so our second idea was this, the ASM. ASM is successfully in finding hidden issues, so we explored the Magenta memory management code and seems feasible to port it. So let's see what happens. But first of all, let's see what is ASM. ASM is relying on a compiler time instrumentation module, which is a platform independent. Basically, it's a dynamic testing tool and using instrumentation, and it can find memory bugs, including buffer overflows, use after freeze. Again, they find many bugs, more than 2,000, including LLVM itself, and also they port it to the Linux kernel, and they also find 65 errors. Yes, in here is the Linux kernel port, which is called KSM. It's a fast and a comprehensive solution for the use after freeze and out of bounds error. It's based on compiling instrumentation, detects out of bounds, reads and writes. It can detect use after freeze easily, and here is a report. Yes. So the header of this report describes what kind of bug happened and what kind of access caused it. So you can see stack traces, and you can also see some memory dumps. And we have to deal with the other one. This is called shadow memory. ASM keeps a large memory region for tracking which buffer are allocated and which should not be touched under normal circumstances. For this, it manages something called shadow memory. Shadow memory maps each original bytes to 1 bit. So whatever you have in original memory, you will have to scale down of 18. So 8 times scaled down the shadow representation. As you see in the figure, this is essentially means that 1/8 of the address space has to be reserved for this. And this is how it goes. So this is how the allocation looks like by using KSM in Linux. The original buffer allocated in the blue area. First, the implementation allocates pages for the corresponding shadow memory. As the second step, the address of the original buffer is translated into shadow. Inside the shadow, the corresponding bytes are set to 0, and this is called unpoisoning. Oh, sorry. So yes, so we have our port working now, which is called MXKSM. Yes, it's so catchy. It's not so catchy. The idea is the C code is Magenta, use this prefix MX, so KSM should be MXKSM. Well, as we mentioned at the start, Magenta is called Zircon. And it's composed of two things, the kernel runtime and the instrumentation. Yes.
Okay, so kernel runtime. This is what the kernel runtime has to ensure. Basically, the most important thing is the implementation of the load and stores inserted by the instrumentation. Obviously, the shadow memory has to be somehow managed, allocated, but it's huge. Actually, you can't allocate physical memory for that. That would be a bad idea. So instead, you have to use some sort of demand paging without breaking VMM. And of course, for the heap, the kernel allocator has to be provided with certain hooks which actually implement the poisoning and poisoning, red zoning, and stuff like that. So what we do is basically we insert the shadow memory range when the kernel init process reserves its memory regions. And this involves creating a VMO, which is a virtual memory object of the corresponding size. And it is marked as shadow. And pages are not committed, of course. So it's an empty promise of pages being committed. So Magenta has these objects which can work this way. So actually, pages are committed when actual memory allocations happen. So under the hood, the allocator that they use is it's optimized for compactness. And it's a very simple one, actually. So we had no trouble with this. Basically, what we do is use the page allocation to poison the whole page in the shadow, corresponding shadow range. And when a chunk is allocated by this allocator, then we just unpoison that one. And if it's freed, we poison it back again in order to be able to detect use after freeze. So this is the code, basically. We just call into our function called mxksn alloc pages, which makes sure that the corresponding shadow range is filled with red zone. And when allocation happens, we actually unpoison those chunks, as I said before. This is the actual function that does the poisoning. We calculate the address mapping first. Then we log the subsequent operations with the mxksn mutex. And after that, pages are brought in by demand, basically, and we issue a page fault operation, which makes the VMO actually commit that physical memory for shadow memory. And it is not visible on this picture, but as the last step, we do the actual mem set that we actually place those red zone bytes there. So let's talk about the instrumentation now. It is an LLVM transformation that we use. Actually, GCC also supports this, but it's harder to work with. It now supports global stack and dynamic allocations, but we only focus on the kernel heap, so dynamic ones. This is the code where it is located in the LLVM tree. It is a bit intimidating to read this code, but it's still possible to hack around. So we found the things that we were looking for. There are two types of instrumentation. Basically, the cheaper one is inserting a function at every place where a memory operation happens, a memory read or write. Now, this sounds like something that can be efficient, but actually it's not quite that bad, so it works. Originally, the Linux kernel patch worked this way, but now they have support for inline instrumentation, which means that these operations are actually inserted in the assembly level, basically. So I don't think I have a zoom here, but these are two code snippets that show the difference. We use only the outline instrumentation so far. So it works out of the box. The only thing we need to ensure that the symbols are actually there when linking the whole thing, but basically that's it. What's harder is actually compiling Clang and LLVM. Initially we started with the mainline ones, but then we figured that actually there's this Fuchsia repo where Google has their own fork and patches. So we were like, let's use their repo and just enable the fsanitize option. And this was easy. But of course, you encounter problems if you aggressively try to instrument the code of the kernel. Because first we were like this, instrument all the things, but then this happened, of course, the kernel panic. So kernels tend to be panicking when you touch something critical, especially in early bring up code. So what can you do? You can sort of do some trial and error, but instead, we were like, let's write some couple of lines of Python, pick a target object file, and instrument it, and we have these in QEMU, so we can boot it up and check whether it outputs anything. So perform linking, boot up the kernel in QEMU. If it doesn't work, just revert the change and go to step 1, choose another target file, and this way we actually instrument a high percentage of the Magenta kernel. So what remains to be done is some demo, which will hopefully work. There's this test lib, also in Linux, and I ported this as well. So here are 3 simple functions with some famous problems with them. So this is out of bounds write on the right after the buffer. This is an out of bounds write on the other end. And we have use after free. So the buffer is allocated, freed, and then used again. So let's try to do this. And this is the point where things might get a little bit tricky. Oh. Sorry. So let's run the ARM64. So actually, they have a build for x86 and ARM64, and we basically use the ARM64, but our code builds for both of the architectures. So this is how it boots, and there we are. So this is the shell. It has ls, stuff like that, ps, as I mentioned earlier. And what is interesting for us are the following parts. So we inserted into the kernel init process this test module, the code that I just showed you, calling this 3 simple functions. And what we have here is basically mxksn reporting these errors correctly. So you've got the out of bounds read, you've got the stack trace, and you don't have symbol names yet, but here are the PC addresses. And here you can see the shadow memory. So the zeros correspond to allocated memory, and something else starting with F is poison bytes. So here we try to read on this byte, and there was a FF at this point, which means that in the original mapping, this was an out-of-bounds read. We also have use after free here. Same thing, basically. FF here, FC, these are ranges that shouldn't be touched. And the shadow memory correctly keeps track of those. So this is how it looks like. This is also how it looks like in Linux. So this is what we have. And of course, this can be used to reveal those type of security issues which shouldn't cause a crash on their own. But using mxksn, you will be able to identify these problems. Okay, so what remains to be done is finding my slides. We have some future work of implementing this to work with stack and globals as well. And hopefully we will be able to get our patches upstream. So I had exchanged some words with this guy called Dmitry Vyukov, who is the original author of these things in the Linux kernel. and he told us that our work was interesting, and we should try to make the fuchsia developers accept our changes. But of course, we can't really code at the level of clarity as Googlers do, but we'll try our best to get these changes upstream, because eventually I'm sure that they would have developed these things on their own. So we basically covered how Magenta works, kind of. We looked at these two tools that we try to port, and hopefully if you encounter in the future some weird operating system, you can think about doing these things, that maybe looking at system calls, or if the OS doesn't have ASN support, you can try to port it as well, because it's not so hard. So thank you very much, and I'm not sure if we have a speaker's corner, or do we have time for questions? Feel free to. Actually, thank you very much, and see you, and you can ask any questions.